Hi everyone, this is Roy Yates, and this is the first lecture in the video instruction, remote instruction version of ECE 226, Probability and Stochastic Processes. We'll start off with a review of continuous, uniform, and exponential random variables that was at the end of our last in-person lecture. Continuous uniform random variable is uniform in its density function from over the interval from A to B. If we sketch this, it looks like a box starting at A with constant density all the way to B. The first example we solved this was the spinning pointer. From section 4.1. In this case, A was equal to 0 and B was equal to 1. The height of this PDF is 1 over B minus A because the PDF has the property that the area under the curve is always equal to 1. And if the width is B minus A, then the height has to be 1 over B minus A. The expected value of this random variable, we remember we integrate x times the PDF for all x. And since the PDF is 0 before A and after B, we get the integral from A to B of x 1 over B minus A dx. And this is equal to B squared minus A squared. And this simplifies, if you remember the formula for the difference of perfect squares, to B plus A over 2. So the expected value is exactly at the midpoint of the PDF. If we did a more complicated calculation, you could show that the variance, which is equal to x minus its expected value, the whole quantity squared, integral of the PDF, which is A to B x minus A plus B over 2 squared, 1 over B minus A dx. And with some algebra and a little calculus, you can show that this is B minus A squared over 12. This theorem summarizes the expected value and variance properties of the uniform random variable. It also reminds us that the CDF of a uniform is a ramp function. So if we plot the CDF that's shown here, we start at A, we go to B, the function is 0 below A, and at A it grows in a straight line. At B it's equal to 1, and then it's flat. This is the CDF with a capital F. Right. And if we take a derivative of that, we rederive the PDF. So the PDF is the derivative of the CDF. And we can do this graphically by remembering that the derivative is the slope. Here's A, here's B, here's the PDF. Below A, the slope is 0. Above B, the slope is 0. And in between, the slope is constant. And it's 1 over B minus A because the rise is 1 and the run is B minus A. Before moving on, let's just recall that the standard deviation is the square root of the variance. And that's exactly b minus a over square root of 12. And the point here to remember is that the standard deviation measures the spread of the distribution around the expected value. And in this case, the spread of the uniform distribution is exactly proportional to the difference b minus a, the spread of this PDF function. In our last class, we also introduced the exponential random variable. And here we summarize its properties in terms of the CDF, the expected value, and the variance. You might look at this CDF and think it looks unfamiliar, but if you take a derivative for the PDF, what we obtain is going piecewise, is that we get the derivative of 1 minus e to the minus lambda x, and that derivative is minus lambda e to the minus lambda x, for x greater than or equal to 0. And otherwise, the derivative of 0 is still 0. And now here we get the way we learned the PDF in the first place as of the exponential random variable as the decaying exponential. And if we sketch a picture of this parameter lambda is always greater than 0. And you want to think about this, whether how this looks when lambda is big or lambda is small. When lambda is big, the PDF, the exponential decays very fast, goes to 0 very quickly. So this is large lambda. But when lambda is small, the exponential decays very slowly. This is small lambda. And it looks funny that these lines cross, but what you have to remember is that for each PDF, the area under the curve is always equal to 1. So when lambda is small and the decay is slow, the peak value at lambda at x equals 0 also has to be low. So this is the height here is lambda, and lambda is small. And here the height is lambda, and lambda is big. Let me label this. Right. In both cases, whether it's the blue curve or the black curve, the area under the curve is 1. And the next point to remind you is that the expected value, which we showed last class, is by integration by parts, is 1 over lambda. So when lambda is large, 1 over lambda is small, and here is the expected value for large lambda. On the other hand, for small lambda, here is the expected value, 1 over lambda when lambda is small, 1 over lambda is big, and the expected value can be as large as you like when lambda is small. And similarly, this is reflected in the variance. So the variance is 1 over lambda squared. And once again, the standard deviation, so sigma x is the square root of the variance of x. It's equal to 1 over lambda. And we see that 1 over lambda is measuring the spread of this distribution. For instance, in the black case, when lambda is big, the spread is very little, and 1 over lambda is small. And in the blue case, this lambda is small, 1 over lambda is big, and not only is the expected value big, but the spread of the distribution around the expected value is big. Last class, we talked about the key property of an exponential random variable, that it's memoryless. And so this is a confusing topic, and so it's worth doing over again. So suppose x is the time you wait at a bus stop, right? And x has the exponential PDF lambda e to the minus lambda x for x greater than 0, 0 otherwise. So consider the base situation is that you arrive at time 0 and you ask what's the probability I wait for a time of at least t. So it's the probability that the time you wait x is going to be greater than t. Well, we can calculate that. It's the integral of t to infinity of the PDF, which is the integral t to infinity of lambda e to the minus lambda x. And this is minus e to the minus lambda x evaluated at x equals t and at x equals infinity. So this is 0 minus minus e to the minus lambda t, e to the minus lambda t. So exponential random variable x has a decaying exponential probability e to the minus lambda t that you wait for more than time t. So now consider the situation. Suppose you have waited for time t0. And the question you're interested in is what is the probability that you wait an additional time t? So it's the probability that x is greater than t0 plus t, given that x is greater than t0. So t0 is what you've already waited, and now it's the probability you wait at least t0 plus an additional t, given you've already waited t0. So the way to solve this problem is that you think of this as event A, and this is event B, and you go back to the definition of conditional probability from the beginning of this semester. It's the probability of A and B over the probability of B. And now we make the observation that the event A is contained in the event B. That is, if A occurs, that x is greater than t0 plus t, then you know that x is greater than t0 for any positive t. So the fact that A is contained in B, this implies that A intersect B is equal to A. And so our probability becomes P of A over P of B. And this is the probability that x is greater than t0 plus t, given the probability x is greater than t0. And now we observe that each of these terms in the denominator and in the numerator are variations on the expression here that we found for the probability x is greater than t. Specifically, we can show the numerator is e to the minus lambda t0 plus t, and the denominator is e to the minus lambda t0. So simplifying this, we get the e to the minus lambda t zeros cancel, and we get e to the minus lambda t. And what this shows is that the probability x is greater than t0 plus t, given x is greater than t0, is exactly the same as the probability x is greater than t. So this is the idea that x is memoryless. The fact that we have waited for time t0 is irrelevant to how much longer we're going to wait. So we show up at time 0 and we ask, what's the probability we wait at least time t? And that this probability we showed right at the beginning is e to the minus lambda t. And now instead, we wait at the bus stop for a while. We have this history. We've already waited time t0, and how much longer are we going to wait? And the answer is it's also going to be the same decaying exponential, e to the minus lambda t probability we wait time t. And that's the heart of being memoryless. To wrap up this review, there's one more random variable that we talked about, which was the Erlang random variable. And the PDF is as shown here. It has parameter n and parameter lambda. The lambda parameter is kind of the same as in the exponential random variable. It represents a kind of a rate, it's positive, and n is an integer. And for the moment, the thing to know is that if you plot this random variable, this PDF, you'll get a function which at 0, it's 0. And then it kind of grows steadily, reaches a peak, and then the exponential part of the function causes it to decay rapidly. You can show that this distribution, this PDF, has a peak at n minus 1 over lambda, and you might think, oh, that's the expected value, and but it isn't. It's close. Instead, if you actually do the calculation of the expected value, right, you would be like, oh, this is 0 to infinity x lambda to the n x minus 1 e to the minus lambda x over n minus 1 factorial dx. And either you can do integration by parts many times, I think n minus 2 times specifically, or you can use some trickery to show that this integral is equal to n over lambda. And so the expected value is in fact a little bigger than the place where the PDF has its peak. You also might note that this random variable has kind of a bell-shaped curve to it. And that's not a coincidence. It has something to do with adding up lots of exponential random variables. And we'll kind of explore this more after we learn about Gaussian random variables. So we're going to stop this video here. My friends have told me you should never make a video that's longer than 15 minutes. I think we're already way over that, but we'll stop here and continue next with Gaussian random variables.